Alright class, so here is the answer key and I guess video for the test review. So let's start off with comparing and contrasting molarity and pH scale. How are they same and how are they different? Okay, so what molarity is, get my pen here. Okay, so molarity is going to measure the concentration of the acid or base. So that is how much acid or base is in the solution compared to water. Well, pH is going to measure how strong if I could spell how strong that acid or base is. And we have the pH scale, and obviously 1 is going to be a very strong acid, and a strong base would be at a 10 to 14 range. And with molarity, when we talk about concentrations, 12 molar is going to be the strongest acid or base, and 0.0001 would be the least strongest acid or base. Okay, they're both going to measure acids and bases though, but it's just from kind of looking at pH scale is going to measure the concentration of H plus ions, and then molarity is how much water to acid or base there is. So what is a buffer, and how would it be used in the lab when there is an acid or base spill? Okay, so a buffer is going to be something that's going to neutralize a reaction. So if we have a strong acid, what we're going to put on it is baking soda. And if we have a strong base spill, then we use vinegar. Explain why water is neutral in the role of molarity of acids and bases. So the reason water is neutral is because it is going to, if we break up water, which is H2O, but it can also be written as HOH. If we break that up into its ions, it's going to be H plus and OH. And whenever we break that up, we're going to have equal amounts of H plus ions and OH ions. So then that's why it is neutral. What is the pH of the following hydrogen ion concentrations? Is it an acid or a base? So when we're doing these pH concentrations, we can just go ahead and pull this number down doing the anti-log, so it's going to be 9. So if it's a pH of 9, that means it's going to be a base. This would be a pH of 2, so that's going to be an acid. And pH of 12, which would also be a base. Next, we have a chemistry teacher is making solutions for a lab, and it calls for 250 milliliters of 1.5 molar H2SO4, but the teacher only has 500 milliliters of 6 molar H2SO4. How much 6 molar H2SO4 would the teacher need to make what the lab calls for? And this is the molarity calculations, where we have molarity of whatever we need times the volume is equal to the molarity of what we have times the volume. Okay, so we need to know how much 6 molar we have, or how much 6 molar we need to make this. So this is what we are going to make. So we can go ahead and put 1.5 here. I'm going to multiply that by 250 milliliters because that's how much we have to make. And then we have 6 molar here. And we don't know how much we need to make. So then we can go ahead and multiply. So 1.5 times 250 is equal to 375. Divide by 6 onto each side. So we should use 62.5 milliliters of 6 molar acid to make that. The next one is, what are the 6 types of chemistry? Explain the 6 types of chemistry. So for the first one, it's biochemistry. Bio meaning life, so that's anything that has to do with life and chemistry. So it's medical. Then I have organic, and I loved organic in college. And that's anything that has to do with carbon-based molecules. I have nuclear, which is going to be anything that's with the sun or solar. I have inorganic, which would be anything besides carbon, so everything else on the periodic table. Physical, which is going to be with physics and chemistry. And then analytical. And analytical is going to tell you how pure it is. So looking at how pure measurements are. Or substances, I guess would be better. Substances are. Next it says, compare and contrast the properties of liquids and solids. Tell how are they the same, tell how they are different. So if you're looking at a solid, solids are going to not have any movement. They're going to have a solid structure. These particles aren't going to be moving a lot. And they do have a definite volume. So no movement. Little or no movement, I should say. And they're going to have a definite. Whereas liquids are going to be a little further apart. They're going to be able to move and bounce off of each other. So they're going to have movement. But they as well have a definite volume. Next one, it says interpret the phase diagrams and answer the following questions. So it says, at which temperature is the triple point? So our triple point is right here. Remember that triple point is going to tell us if it's a solid, liquid, or gas. We really can't determine which phase that it is in at that triple point. So if you look down, the temperature is at a negative 56.4. Then at what pressure, at what range, so a range of pressure, so that means you should have 2 numbers here. And at what range in pressure does a solid exist? So right here we can go from a solid, which is down here at 0, all the way up to 73. See how it's a range of numbers? It can be anywhere between these. It can be a solid. At what temperature and pressure increase to their limit on the chart? What state of matter is it? So if we're at the pressure and temperature is increased to its almost limit, that's going to be the supercritical fluid. Oh, or you can say point as well. Supercritical fluid or supercritical point. Next is it says explain the following phase changes. Use the words and show how they are connected. I like to do mine in a little triangle so you can see how each one is connected, but we're going to have solid here. So that one's gone. Show that going to liquid, You're going from a solid to a liquid first. That is going to be melting. Going from a liquid to a solid, that is going to be freezing. Liquid to a gas is going to be It's going to be evaporation. Gas to a liquid is going to be condensation. Gas to a solid is going to be deposition. And solid to a gas is sublimation. Okay, so condensation's gone, deposition's gone, vaporization is the same as evaporation. We have gas, sublimation. Okay, last thing is plasma. And what plasma is a charged liquid. So fluorescent light bulbs are made of plasma, and when they are ionized, so ionized, they are carrying a charge. That's what ionized means. When they are ionized, that means, or ionization, that means they have a charge, so that they're going to be able to carry electricity. When they become deionized, they no longer carry that charge, therefore they're just a liquid. So there's all those words and how they interconnect. Name the separation techniques and describe each of them. I'm only going to do 4 for you. That should be sufficient enough. I know there's 6 of them, but I'm just going to talk about 4. We have, first of all, we have evaporation, which is going to, you can go ahead and separate a liquid from a solid. I guess, or 2 liquids as well. We can do filtration, and this will separate a solid from a liquid. Then I have distillation, and this will actually pull out ions from a liquid. So we have distilled water. Decanting, we did this in our lab, and that'll pull out a solid from a liquid as well. There's also magnetism, using magnets. Chromatography, which will separate atoms by color. Trying to think off the top of my head. That's a lot of them for right now. Next is naming the 4 types of crystals and explain each one. The first one is going to be covalent network. And that is going to be, say if we have silicon dioxide, this is going to form a network of crystals between these 2 atoms. Then we have ionic. Ionic forms crystals between positives and negatives. So if we have a positive, and then we have a negative, and then we have a positive. Oh, this should be negative. And we have a positive here. So this right here, this attraction between the positives and negatives on each one is going to form the ionic crystal. So that's an example, it would be like table salt. Then I have covalent molecular. And the difference between these 2 ones is going to be that, so if we have water, is attracted to another water molecule, which is attracted to another water molecule, which is attracted to another water molecule. So it's in between molecules. This is inside of a molecule, this right here, but well, this one's between two molecules. And then the last one is metallic. Metallic has a sea of electrons. So it's going to be, say, copper, and we have another copper. It'll actually make a crystal because of the electrons. This one I already did, so you can go ahead and cross that one off. Okay, give three examples of qualitative data and 3 examples of quantitative data. So qualitative is going to be a description. So like color, size, how it smells. Okay, while quantitative is a quantity. So that is going to be a number. So that's going to be like the temperature, the mass, the volume. Compare and contrast accuracy and precision. Precision is going to be one. It's going to be, well, I guess it'll be a set of data. So one set of data. So if we have, say we did our experiment in class and there's 17.5, someone got 17.5, someone got 17.9, and somebody got 17.8. We're going to look at that whole set on how everybody did. For accuracy, is looking just at one measurement. So say if I say Billy did this one, and now we're just looking at how accurate Billy was to what he was supposed to get. So we would just be looking at 17.5, nothing else. Next one is calculating percent yield and percent error for each group. So the first step here is we have our starting mass, so we need to find our ending mass. Well, how do you get that? You're going to subtract the weight of the beaker and the copper minus the beaker to get just the copper to find out what we ended with. So if we have 31.470 minus 26.571, we get 4.899. And then if we have 60.100 minus 57.233, get 2.867. Okay, so we're going to calculate the percent yield first. So percent yield is going to be our actual over our theoretical. So our actual is what we got in the experiment, and the theoretical is what we started with. So we should get 4.899 divided by 5.003. Plug it into your calculator. 4.899 divided, not times. 4.899 divided by 5.003. I got, and then times it by 100. 97.9%. And then do the other one, which is going to be 2.867 divided by 5.017. We got 57.1%. So which one would have the best results? It would be trial or group 1, because they were closer to 100. When you're doing percent yield, the closer you get to 100%, the better. Now calculating percent error. Percent error, you want to get closer to 0. So when you're doing percent error, you actually take your theoretical, which is what you started with, minus your actual over your theoretical. So we should go 5.003 minus 4.899 divided by 5.003. 5.003 minus 4.899 equals divided by 5.003 equals times 100. I got 2.07%. And then we'll do the other one. So we should have 5.003 minus 2.867 divided by 5.0. Oh, it should be 5.17, sorry. 5.017. 5.017 minus 2.867 equals divided by 5.017, 42.8. So which groups are precise? Well, obviously this one's going to be more precise when we're comparing the two, because this one's closer to 0 and is either or both groups accurate, and this group would be more accurate as well because it's closer to 0. Next one's going to be the independent and dependent variables, and what that is. The independent one is normally the one that excuse me, the dependent variable is going to depend on what we change in the independent variable. So this is going to be what we change, and this is the outcome of the change. Remember, constants are going to be anything that does not change. And then a control, we'll talk about that when we get there. So it says a firefighter is trying to figure out which type of fire extinguisher, CO2, water, or dry chemical will put out the fire the fastest. Think about the issue being tested and imagine an appropriate experiment to determine what type of fire extinguisher can extinguish fires the fastest. Then identify the key elements in the experimental design below. So our dependent variable, what we were trying to figure out is time it takes to put out the fire. That is our outcome. That's what we are trying to measure. Our independent variable is the type of fire extinguisher. Okay, 3 variables that can be held constant, so that's something that's not going to change at all. So that could be the time that we use the fire extinguisher. It can be how big the fire is and what we use to start the fire. That means each experiment we're going to hold it the same. A control is a group that we're going to look at and compare it to. So this would just be letting the fire burn. So we can just let the fire burn and see if it naturally goes out and see how long it takes it for it to go out. Okay, the diameter of a carbon atom is that long micrometers. What is the best way to express a number? We need to put this into scientific notations because we don't want to write all those zeros. So we can go ahead and move the decimal, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 5.644 times 10 to the negative 8th. It's negative because we moved it to the right, so it's going to make it a negative exponent. And then micrometers is mu and then m. That's how it should be expressed. What is the result? Adding 6.5 times 10 to the 5th and 2.5 times 10 to the 3rd. Okay, so we're going to add these two numbers. If we're adding the numbers, we have to make the exponents the same. So we have 5 and 3. So what we need to do is we need to move one of the decimals. I like to go to the biggest decimal, so I'm going to move this one, trying to make this number bigger, so this number has to get smaller. So by 2 times. 1, 2. And 2 times because if we go 5 minus 3, it's going to give us 2 times. We have to move it. Then we can align the decimals and add it. So if we have 6.5, we have 0.025, and we're adding them together, we should get 5256 times 10 to the 5th. Now sig figs and sinot, we have one number, then the decimal, so sinot is okay. Sig figs, we should only have 2 sig figs. So we should have 6.5 times 10 to the 5th. Now what about multiplying? Multiplying is a little bit easier because all we have to do is add the exponents here. We can go ahead and we multiply the numbers, add the exponents. So 2.5 times 3.5 equals 8.75, and we can go ahead and add those exponents. If we go 7 plus a negative 8, it gives us negative 1. We only have 2 sig figs here, so we're going to go ahead and have to round that up, so we only get left with 2 numbers here, so our answer is going to be 8.8 times 10 to the negative 1. Now subtracting scientific notation. Subtracting is like adding. We have to make sure that these are the same first. So this is at 4, this is at 5, so I'm going to go ahead and make this number bigger, so make this number smaller. So we're going to move it back one. So we're going to go 0.55 minus 8.5. Gives us a negative 7.95 times 10 to the 5th. We do have 2 sig figs here, so this is going to round that up, which is going to make it into 0, which is going to round that up. So our answer would be 8.0 times 10 to the negative 5. And remember, that's negative. Remember, we're subtracting something very, very small to something that's big, so of course our answer should be negative. Now when dividing it, you can go ahead and divide these numbers out, and we're going to subtract the exponents. So if we go 6.7 divided by 9.4, gives me 0.7127. And it's going to be times 10. Okay, if we have a negative, or if we have a 24, minus a minus 14, that changes this to a plus 14. So we have 24 plus 14, that gives us 38. Now, is this in correct scientific notation in sig figs? No, we only have 2 sig figs, and we have to move it so that there's a number, then the decimal. So we're going to move this decimal back, making this number bigger, so that has to get smaller, and we can only have 2 sig figs, so it's going to be 7.1 times 10 to the 37th. Next one, volume. Everybody forgets that volume is also equal to length times width times height. That's how you can find volume. So go ahead and calculate this. It's all in meters, so it's going to be meters cubed. And we're multiplying everything, so it should be 2.44 times 1.4 times 8.4 gives us a number. And then we can add these, a negative 2 plus a negative 3 plus a negative 3. So I know my exponent is 3 plus 3 is 6, plus 2 is negative 8. We can go 2.44 times 1.4 times 8.4 gives us 28.694. We only have 2 sig figs. This one has 2, this one has 2, and this one has 3. So we have to go with the lowest number of sig figs. We can only have 2 sig figs. It's going to round that up to 9. We have to move the decimal over, making this number smaller, so this has to get bigger. So I know a lot of you get confused. Remember, negative 7 is bigger than negative 8. So it's going to be 2.9 times 10 to the negative 7th meters cubed. Next one is using the volume above, calculate the density. Remember, density equals my love, but it breaks my heart every time, so mass over volume. So we have 3.75 times 10 to the negative 5th grams over 2.9 times 10 to the negative 7th meters cubed is equal to density. So we can divide those two. I get 1.293. We have 2 sig figs, so our answer can only have 2 sig figs. So we can go ahead and round that, so it's going to be 1.3. And then we have a negative 5 plus 7 gives us 2 times 10 to the second. It's going to be grams per meter cubed. Remember, the reason it's to the second is because if I have a negative 5 and I'm subtracting a minus 7, this changes to a plus. Next one is, what is the mass of 8.09 times 10 to the 5th micrograms cubed of alcohol if the density of alcohol is 0.70 grams per milliliter? So the first thing I like to do is, when you're looking at these problems, is let's look at our mass. We don't know our mass, that's what we're trying to find out. Next we have our volume. I already know it's a volume because it says it's cubed right there. So it's going to be 8.09 times 10 to the 5th micrometers cubed. And then our density is equal to 0.70 grams per milliliter. Okay, so are these in the same unit? No, they're not. So we have to convert one. We can either convert this to grams per micrometer cubed, or we can convert this to milliliters. And I think it's easier to go to milliliters, sorry. So first step, we're going to start off with what we're given, which is going to be 8.09 times 10 to the 5th micrometers cubed, and we have to go to centimeters cubed because that's a conversion factor. I know that 1 centimeter cubed is equal to 1 milliliter. So, and it's cubed, so we're going to have it 3 times. Think of the box. We have micrometer times a micrometer times the micrometer. So it has to happen 3 different times. So I know that there is 1 times 10 to the 6th micrometers times 1 times 10 to the 6th micrometers times 1 times 10 to the 6th micrometers in 1 meter times 1 meter times 1 meter, because we're doing it 3 different times for this. And then I know that there's 1 meter times 1 meter times 1 meter is equal to 1 times 10 to the second centimeters times 1 times 10 to the second centimeters times 1 times 10 to the second centimeters. And I know that is equal to 1 centimeter cubed is equal to 1 milliliter. So if I have 6 plus 6 plus 6 equals 18, and I know 2 plus 2 plus 2 equals 6, I have 5 plus 6 is 11. Divided by 1 times 10 to the 18th. So it's going to be times 10 to the 11th. 8.09. So what I did here is I added these two together. That's how I got my 11. I added these together. That's how I got my 18. Now I can divide the two, so I know it's going to be 8.09 times 10 to the 11 minus 18 gives me -7 is my volume. So now all I have to do is plug it into my equation. I know that 0.70 grams per milliliter is equal to my mass over my 8.09 times 10 to the -7th. Multiply it by each side. 8.09 times 10 to the -7th. So that's going to give me, put this into scientific notation, makes it easier for me. So it's going to be 7.0 times 10 to the -1. 8.09 times 7.0 equals 56.63. Times 10 to the, we have a -7 plus 1, that's also negative, so that's going to get us to the -8th. We have to make this number smaller, so that number gets bigger, so it's 5.663 times 10 to the -7th grams. But sig figs and psi naught, we only have 2, so that's going to round it up, so it's going to be 5.7 times 10 to the -7th grams. There's my answer. Okay, converting temperature, I will let you look at those formulas. Those formulas are really, really easy, so I'm not going to go through that with you. Picograms to milligrams, that one's pretty easy as well. So if you have questions about those two, come see me in the morning. Same with the bathtub leaking. These are all dimensional analysis. If you're having problems with the dimensional analysis, okay, you can go to the website, here on the website, go to the quantitative basics and go to the test review here. And I literally do all of those problems, pretty much all the same problems. If you scroll down, if it lets me scroll down. I do all of these problems down here on the review. So they are all done there as well. So if you really are struggling with that, go to that website and look at those problems because they're all done there for you. Okay, next is filling out the table below with atomic number. And I actually don't have a periodic table in here with me. Let me grab a periodic table. Okay, sorry about that. So silicon is going to have a mass number of 14 and its atomic number is, oh no, mass number of 28, atomic number 14, sorry, wrong one, wrong element. So its atomic number is 14 here, and then we have cesium, which is CS, and its atomic number is 55. So how do we get the mass number? The mass number, if it does not have a dash behind it and a number, then you have to look at the periodic table. So this one would be the periodic table. You have to look at that one. Periodic table for this one, it's going to be 28.086. This one's going to be 29. The mass number is whatever's behind it. This one's 24. And then cesium is 132.90. So how do we calculate the number of neutrons? The number of neutrons is going to be the mass number minus atomic number. So we can round that. So we're going to go 28 minus 14 gives us 14. We're going to have 29 minus 14 gives us 15. 24 minus 14 equals 10. And then we can round this to 133 minus 55 is 78. Now, protons and electrons are the same as atomic number, so these are the same. Don't forget that. So it'll be 14, 14, 14, 14, 14, 14, 55, 55, 55. Okay, valence electrons. These are going to be the group numbers. And number of shells is the periods. Remember, groups go up and down. Periods go side to side. So for silicon, it is going to have 4 valence electrons all the way down. Doesn't change. Cesium only has 1 valence electron because it's in the first group. Now shells of electrons, it's going to be the period. Silicon is in the third period, so all of these are going to have 3 shells of electrons. And you can do that even by looking at the electron configuration. You can figure out how many shells of electrons it has. And then cesium is down in the 5th period, so it's going to, or the 6th period, so it's going to have 6. Okay, calculate the number of neutrons. Oh, which of the following is written in correct isotope form for the element of nitrogen containing 5 neutrons? So if you know neutrons, if we add the atomic number, that should give us our mass number, which if it's in correct isotope form, it should go the element dash mass. That is isotope form. So if we have 5 neutrons and nitrogen is actually atomic number 7, so the correct one would be nitrogen 12. 5 plus 7 is 12. Percent abundance. It says imaginary element X is composed of 70% of isotope 70 and 30% of isotope 75. Estimate the mass. Okay, so first of all, you have to take this out of the percent, so it's going to be 0.70. And we have to multiply it by the mass of the isotope, which is 70. Then we're going to take 30 out of its percent, which is 0.30. Going to take it out of its percent. If you don't know how to do that, it's 70 divided by 100. It'll give you your decimal. And we have to multiply that by its mass. Then we're going to multiply these all together and then add them up together. So we have 0.70 times 70, which gives us 49. And we have 0.3 times 75, which gives us 22.5, and then we add these two together, so our approximate mass is 49 plus 22 is 71.5 AMU, average atomic mass. For charges of ions, okay, these go by group numbers. If it's in group 1, it's going to be a +1 charge. If it's in group 2, it's going to be a +2 charge. Group 3, or, well, I guess it jumps to 13, but group 3A would be a +3 charge. Group 14 is a plus or minus 4. Group 15 is a -3. Group 16 is a -2. And group 17 is a -1. And group 18 has no charge because of the valence electrons. So calcium is in group 2, therefore it has a +2 charge. Chlorine is in group 17, or group 7A, so it has a -1 charge. The reason it has a -1 charge is because it's going to be easier to gain 1 electron and have 8 valence electrons rather than lose the other 7. Name the element for the following that has 3 valence electrons in the 5th shell. So 3 valence electrons, so that means it's going to be put in group 13, and you can count down 1, 2, 3, 4, 5 into the 5th shell, and that is IN. And then we have halogen, which is going to be group 17. It's in the 6th period, so 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, which is going to be acetine. AT. Highly electronegative element with the largest atomic radius in its group. So electronegativity is going to increase from the left to the right, and it decreases as it goes down. So the most electronegative element is actually fluorine. Now, atomic radius is just the opposite. It is going to, I guess I could draw it this way too. it is going to decrease as it goes from left to right, and it increases as it goes down. So fluorine would be the correct answer there. I think I had that right. Let me double check here. It's been a long day. Periodic table, periodic trends. Make sure I have it right before I keep going. Ionization. Yeah, so it decreases going from left to right and increases going down. Yeah, I was right. Okay, good. Ionization energy decreases going down, increases as it goes left to right. I remember it the other way. I remember it to where everything going from left to right, because that's how we read the periodic table anyway. So if you have questions about that, come see me tomorrow as well. Next part of the worksheet, we're almost done here. So largest atomic size. So atomic size is going to decrease as you go over, but increase as you go down. Okay, ionic size is the same way. It's going to decrease as you go over, increase as you go down. Electronegativity increases as you go over, decreases as you go down. And ionization energy increases as you go over and decreases as you go down. So if we're looking at rubidium and chlorine, okay, chlorine is way further to the right, so that means it's going to have a smaller atomic radius. So rubidium is going to be bigger. And if we're looking at tin and fluorine, it increases as you go down, and fluorine is still way to the right of tin, so tin is still bigger. Now ionic size is going to be the exact same, so we know which one is the same. Now ionization energy and electronegativity are going to be the exact same. So it increases as you go over and decreases as you go down, so chlorine is going to be more electronegative, and fluorine is the most electronegative on the whole periodic table, so I know that. And then these ones are going to be the same as well. This is actually on your tests or on your formative assessment as well on your past test. So these ones are the alkali metals. These are alkali earth metals. These are the transition metals. These are the halogens. These are the noble gases. Okay, so then we have 1A, 2A, 3B, continuing on to 12B, and then we go to 13A, 14A. Sometimes you'll see it like that, or sometimes you'll see 3A, 4A. I'll prefer the 3A, 4A, so then you know the valence electrons, but that's just me personally. And then we have, do I need to label the blocks? Oh, yep. So we have the S block here. We have the D block here. We have the P block here. And we have the F block down there. Next one. Aufbau diagram and noble gas notation for bismuth. Bismuth is Bi all the way at the bottom. It's a lot. Aufbau is going to show the arrows. I'm not going to do it all. I'm going to do noble gas notation. Sorry, I'm cheating. If you're having problems with the Aufbau, with the arrows up, down, and showing how the electrons are feeling, let me know. Come see me. We'll do it that way. But noble gas notation is you need to go back to the noble gas before bismuth, which is going to be xenon. And that's going to take you all the way to xenon. And we can jump down to 6s2. And then we actually go down to the lanthanide actinide series, which is the F block, and it jumps down 2 energy levels, so it's going to be 4F14. And then we can jump back up, which is going to be 5D10, and then 6P1, 2, 3. So for the Aufbau diagram, I guess I could show you up to, I'll do the 6S, which is going to be 1, 2, and then 4F, 1, 2, 3, 4, 5, 6, 7. This is all the 4F block, and these will all have up-down arrows showing the spin of these electrons. And then we have the 5D, and then the 6P. Next is argon on the electron configuration and drawing just drawing electron configuration on the XYZ axis. So you can draw argon. Argon is number 18 on the periodic table, so it's going to be 1s2, 2s2, 2p6, 3s, 2, 3p6. It's a good one to draw. So we have our XYZ axis. So first one is first 1s. Then we have our 2s, 2px, 2py, 2pz. Then we have our 3s. Hoping you can draw the electrons on all these. 2 electrons on the s. And then we have our 3px, 3py, 3pz. And that's exactly how it would look. Now it says label the wave below. I know there's not a wave, so let's go ahead and draw one. So obviously here's the crest, here's the trough, this is the wavelength. You kind of have a medium, I would say a high amplitude here, a lower one over here. Here's a shorter wavelength, here's a longer wavelength. Kind of describing the wave there. And the next one talks about it takes 8.7 times 10 to the negative 19 joules of energy to remove one electron from the gold surface. What is the maximum wavelength of a light capable of causing this effect? Hint, you have to use the two equations. So we're going to have to start off with energy, which energy is equal to Planck's constant times the frequency. So we have to use 8.17 times 10 to the negative 19th is equal to 6.626 times 10 to the negative 34. That's Planck's constant, that's h, times our frequency. Divide by Planck's constant on both sides to get frequency by itself. So if we go 8.17 divided by 6.626 equals 1.233 times 10 to the 19 plus 34, 53 is equal to V, or frequency. Now we're going to plug that into the wavelength equation, which is going to be C is equal to V lambda. So we can go speed of light is 2.998 times 10 to the 8th divided by 1.233 times 10 to the 53rd. So 2.998 divided by 1.233 equals 2.43. 8 minus 53 times 10 to the 61st negative. And that would be our wavelength, which would be measured in joules per meter or nanometer. So those are the two equations that you would use, and that's all it is asking for. Okay. Next, it's cosmic ray of a high energy radiation. What is the frequency of the cosmic ray that has a wavelength of that? Which two types of rays are the cosmic ray most related to? Okay, so we're going to use our speed of light is equal to our lambda v, because we're trying to find our frequency. We have the speed of light, 2.998 times 10 to the 8th divided by 2.67 times 10 to the negative 13th. And I just did that whole thing in my head is equal to v. If you wanted to do it out, it'd be c is equal to lambda v, divide by lambda on each side to get v by itself. So c over lambda is equal to v. Okay, so just so you know where I got that, I didn't just pull it out of nowhere. 2.998 divided by 2.998, it's going to divided by 2.998 divided by, my calculator's messing up. 2.998 divided by 2.67 is equal to 1.17, 1.12 times 10 to the 8 plus 13 is 21. So that is a frequency. So we can actually go to our light emission spectrum and look at what frequency it compares to. So if it was times 10 to the negative, or times 10 to the 21st, it is going to be right in here. So it's going to be relative to a gamma ray. That would be the answer. Alright, so if you have any questions, please come in and see me tomorrow morning. I will be here at 7-ish. So just come on in whenever you